Hello there, students. In this video, we're going to learn about kinematics in 2 dimensions. Previously, we talked about kinematics in 1 dimension, and then we introduced gravity to the mix. When we did this, we only looked at how gravity affected velocities in one direction, either up or down the axis that the gravity vector was on. We couldn't talk about how far a trebuchet could lob a cantaloupe, or how far a ball will travel when kicked, while restricted to 1 dimension. Working in 2 dimensions, however, we can, and we can even use our kinematic equations as long as the separate accelerations in each dimension are a constant. Let's start by choosing a coordinate system where gravity lies only on the y-axis, and we take gravity to be the constant magnitude of 9.81 meters per second squared, just like we've done previously. For inanimate objects like a cantaloupe or ball, the only acceleration acting on them while in flight will be gravity, which is now in the y direction for our coordinate system. These objects' accelerations in the x direction will be 0. Let's go through an example and see what we can figure out and how this works in practice. If we throw a ball with an angle of elevation measured from the x-axis of theta naught equals about 22.6 degrees with an initial velocity, v naught, of 13 meters per second, how long is the ball in the air, and how far does it travel in that time? First, we break down this initial velocity into its vector components. The magnitude, the length of the hypotenuse on this right triangle, was given to us as 13 meters per second. The component of this velocity vector that lies in the x direction, v naught x, is 12 meters per second. Then, the component along the y direction, v naught y, is 5 meters per second. Once this object is in motion, it has no way of accelerating itself, so its y acceleration is just due to gravity, and its x acceleration is 0. Since we know the acceleration in the y direction is solely due to gravity, a sub y equals negative 9.81 meters per second squared. Motion in each dimension, x and y, is independent from the other, so we can work our kinematic equations one dimension at a time. We can look at the y dimension to figure out how long the ball was in the air, which we've done in our previous video about gravity. Since gravity is acting on the ball while in flight, it will eventually hit the ground again, meaning a total vertical displacement, delta y, of 0, since it returns to the same height it was thrown from. What we want to find is a kinematic equation that has a displacement and a time variable so that we can solve for the time variable. How about this one? Here I am using the notation v naught y to indicate the initial y velocity at time t equals 0. Using v sub y might be confusing since the y velocity is in fact changing over time, since the y acceleration is non-zero due to gravity. The total y displacement, delta y, is 0. Then, plugging in our initial y velocity and our y acceleration, we can solve for time t, which we find is equal to 1.02 seconds. Now we can focus on the motion in the x dimension. To answer the second question, how far does the ball travel during its flight time, we need to find a kinematic equation that has displacement and time in it again. How about the same equation, but for the x variable? We see this equation has an acceleration term in it, but since we're working in the x dimension, which has no acceleration, this term is 0, which makes things easy for us. We've calculated the initial x velocity already, and we've just found its air time, t. Plugging this in, we find a total displacement in the x direction of 12.24 meters. Here's a quick visual of how the velocity components are changing over the trajectory. The initial x velocity remains unchanged throughout because there is no x acceleration. The initial y velocity decreases and then becomes negative as we'd expect due to the effect of gravitational acceleration in the y dimension. And the velocity in the y direction is momentarily 0 at the top of the trajectory. The total velocity vector at each point, being a vector addition of the two separate components, looks like this. It follows the arcing trajectory, where the total velocity v is always tangent to the curve itself. Now that we're introduced to kinematics in more than one dimension, we can start looking at a lot of other things, like how to maximize the range of a trebuchet, or how to calculate the maximum height of a projectile, or how things in orbit stay in orbit. In the next few videos, we'll start covering these interesting topics, so stay tuned. Thanks for watching and learning about physics. If you have a question, drop a comment or head over to my Facebook page in the video description.